What do your phone, your car, your headphones, your smartwatch, and even medical scanners all have in common? They all depend on one invisible idea: signal processing. And if that sounds abstract, here is the surprising part. Signal processing is basically the art of turning messy real-world information into something useful. It helps us pull voices out of noise, detect problems before machines fail, and even make sense of data that would otherwise be overwhelming. So in the next few minutes, let us break down 5 essential signal processing concepts that quietly power modern technology, and more importantly, why they matter. First, sampling. Real-world signals are continuous. Your voice, a heartbeat, a vibration from a motor, they happen smoothly over time. But computers cannot handle continuous. They need snapshots, that is sampling, taking measurements at regular intervals. Why is this useful? Because once a signal is sampled, it can be stored, analyzed, compressed, and transmitted. For example, when you record audio, your microphone captures thousands of samples every second. The higher the sample rate, the more accurately you can preserve the original sound. But there is a catch. If you sample too slowly, you can create false information in the data. That is why sampling rate matters so much in audio, medical devices, and communications. Next up, filtering. In the real world, signals are rarely clean. They are mixed with noise, interference, and unwanted frequencies. A filter removes what you do not want and keeps what you do. That is useful everywhere. Noise-canceling headphones use filtering ideas to reduce background sound. In medicine, filters can help isolate the important parts of an ECG signal. In factories, they can remove sensor noise, so a machine's vibration data is easier to interpret. Mechanically, filters work by emphasizing certain frequency ranges and suppressing others. Think of it like a sieve, but for information. Now for one of the most powerful ideas in all of engineering, the frequency domain. Instead of looking at a signal as it changes over time, you can also look at what frequencies it contains. That is incredibly useful, because many problems are easier to spot there. For example, if a machine is vibrating at an unusual frequency, that can indicate wear or imbalance. If a music file has too much energy in a certain range, an audio engineer can adjust it. And in wireless communication, frequency analysis helps separate useful signals from interference. This is the reason tools like the Fourier transform are so important. They let engineers see hidden structure inside complex signals. Next is convolution, a word that sounds intimidating but shows up everywhere. At its core, convolution describes how one signal interacts with another. It is the math behind filtering, blurring, sharpening, and many forms of pattern detection. In image processing, for example, a convolution can detect edges in a photo. In audio, it can simulate how a sound would behave in a room. In control systems, it helps engineers predict how a system responds over time. So if sampling gets data into a computer, convolution helps the computer transform and interpret that data. Finally, the time-frequency trade-off. Sometimes signals change quickly. Sometimes you need to know exactly when something happened. Other times, the exact frequency is more important. You usually cannot optimize both perfectly at once. This matters in applications like speech analysis, seismic monitoring, or radar. If a doctor wants to detect a short abnormal event in a heartbeat, timing matters. If an engineer wants to identify a narrow band interference in a radio signal, frequency detail matters. The key idea is this: signal processing is always about choosing the right view of the data for the job. So those are the 5 essentials: sampling, filtering, frequency domain analysis, convolution, and the time-frequency trade-off. Together, they form the backbone of modern engineering. The real beauty of signal processing is that it takes the chaos of the physical world and turns it into something we can measure, improve, and trust. And once you start noticing it, you realize it is everywhere, from the music in your earbuds to the sensors in a self-driving car. If you want, I can also turn this into a version with on-screen visuals, B-roll cues, and a tighter YouTube retention-focused structure. Signal processing in engineering. 5 essential concepts that power modern tech is just one small part of signal processing. If you are interested, our full free signal processing course is linked in the description.